Welcome back to ChemExam Explained, where the aim is chemistry clarity, exam mastery. In this video, we will be looking at Chem Chemistry Paper 2, Unit 2, Module 2, 2025. Let's begin. 2, Part A. Electromagnetic radiation consists of waves that have electrical and magnetic properties. There are different types of radiation. Draw a diagram to show the approximate wavelength ranges of any three types of radiation, which are found in the electromagnetic spectrum. So three simple ones would be your visible region, your UV region, which is below your visible region, and of course IR, which is above your visible region. So you go from your short wavelength to your long wavelength. And so our ranges are 10 nanometer to 400 nanometer for UV, 400 to about 780 nanometers for the visible region, and 780 to about 1 millimeter for your IR radiation. Part B. The energy of an electronic transition has a frequency of 1.01 times 10 to the 16 Hertz. Calculate the energy of the radiation emitted. So we're going to use E equal H nu or V. Our small v here is nu, which is frequency. H represents Planck's constant, which is 6.63 times 10 to the minus 34 joules second. And of course, our frequency, which is Hertz, is the same as per second. So it's 1.01 times 10 to the 16 per second. We then calculate the values by multiplying them, and our answer for energy is 6.70 times 10 to the 18 joules. 2 Part C. Figure 3 shows the electronic transition within a molecule. Some compounds absorb UV-Vis radiation, resulting in electronic transitions within the molecule. So here we have our diagram without the arrows. So the arrows were placed in. I'll explain the arrows shortly. It depends on the type of molecule. You might have a sigma to sigma star. You might have sigma to pi star, and then pi to sigma star, pi to pi star, then N, which is their non-bonding or lone pair electrons, to sigma star, and N to pi star. So on figure 3, draw the possible transitions associated with the absorption in this UV-Vis region of the spectrum. And so because they say the transitions associated with the absorption, all of these are possible going from your sigma to sigma star, sigma to pi to sigma star, pi to pi star, n to sigma star, n to pi star. But what is allowed are the ones that are low in energy. So the lines that are closer together are the ones allowed. So pi to pi star is allowed, n to sigma star is allowed, and n to pi star is allowed. So these are the transitions that are associated with the absorption in this UV-Vis region of the spectrum. Part D. An experiment is carried out to determine the concentration of copper 2 plus ions in a sample of well water. A measured volume of the water is treated with excess ammonia, and a sample of the resultant solution was analyzed in a cuvette of side 1 cm at a wavelength of 615 nanometer in a UV-Vis spectrophotometer. Part 1. State what would be observed when ammonia is added. So here we have our aqueous ammonia added to our copper ion, forming a complex of tetraamine copper 2 ion, which is a blue complex. D Part 2. Give the reason why the wavelength of 615 nanometer was chosen. Now let me show you the range for the visible region. Here, Roy G. Biv. And so you'll notice that within this region, having a blue complex, that would give us our maximum wavelength. So 615 is the maximum wavelength, lambda max, at which the complex absorb radiation. Part 3. Describe how a calibration curve can be made and used in the analysis process. So first thing you have to do is to prepare copper 2 plus ions standard solutions. You are then going to measure the absorbance of each of the standards. We are going to use the results of concentration and absorbance to plot a calibration curve and then use the sample absorbance to find the concentration on the calibration curve. Part E, an aqueous solution of copper 2 plus ions at a concentration of 2.5 times 10 to the minus 3 gram per dm cube was analyzed using a cuvette of path length 1 centimeter in a UV-Vis spectrophotometer. E part 1. Calculate the concentration of the known copper 2 plus ion in mole per dm cube. So the value given here is mass concentration. And so in order to find the molar concentration, we're going to use the formula mass concentration equal molar concentration times molar mass. Then solve to make molar concentration the subject of the formula. So the mass concentration given is 2.5 times 10 to the minus 3 gram per dm cube divided by the molar mass of 63.5 gram per mole, which you can find from our data booklet. And then we work out the molar concentration to be 3.94 times 10 to the minus 5 moles per dm cube. E part 2. Applying Beer-Lambert's law, calculate the molar absorptivity, which is E, using the stated absorbance values. Now, we are to work out E, but in order to calculate E, we need to know the concentration, we need to know the path length, and we need to know the absorbance. But the question stated that the absorbance value was given, but we don't see an absorbance value. So we'll use the factor A. And we're saying now, let's make E the subject of the formula. So E is equal to A over Cl. We know the concentration and we know the path length to be 1. So A, which was supposed to be given, divided by concentration times path length, should give us a value. But because we don't know A, we can't work out a single value. But our unit works out to be dm cube per mole per cm cube. So the value of E is our A, which is supposed to be known, over the concentration times the path length. So in part 3, a well water sample containing copper 2 plus ions was also analyzed using the same cell of path length 1 under the same conditions in the spectrophotometer. The absorbance was 0.350. And we were to calculate the concentration of the copper 2 plus ions in this sample. So here we're going to use the molar absorptivity to calculate the concentration. But remember, we don't have a single value. So we're going to use the factor that we worked out for E to just plug into this equation. So we make concentration the subject of the formula. So conc is equal to absorbance over the molar absorptivity times the path length. And so in this case, we know the absorbance to be 0.350 divided by E. And E is our A that was known, or supposed to be known, divided by the concentration times the path length. And so we simplify that by saying 0.350 divided by A times the concentration, which is times 10 to the minus 5. And so our concentration is equal to 0.350 divided by A, which was supposed to be known, times the concentration. And if we had known or given the value for the absorbance in part 2, we will get a single value, and our concentration would be in moles per dm cube. Part F. Outline the steps in analyzing a sample using UV-Vis spectroscopy. Well, first of all, we have to prepare the sample. Then place it in your cuvette. You are then going to select the wavelength because it must be monochromatic light. So that's light of a single wavelength. Then you're going to zero your instrument with a blank, which is deionized water. After that, you're going to measure the absorbance and then compare the absorbance of the sample using the calibration curve. Part G. Explain the principles of infrared spectroscopy. Where molecules absorb IR radiation causing vibration, and those vibrations are stretching or bending vibration, and these are characteristics of the functional group. So note that IR radiation is not sufficient to cause electronic transitions. It can only cause the molecule to vibrate. And the two types of vibrational frequencies are stretching and bending. Part H. Figure 4 shows a diagram of compound D, which has the molecular formula C5H8O. Infrared spectroscopy was used to determine the structure of compound. And this is the structure of the compound. So you notice we have a carbon-carbon double bond and we have a carbonyl group. Part HI. Compound D exhibits characteristics absorbance wave numbers 1695 per centimeter and 1619 per centimeter. In the infrared spectrum, indicate the functional group responsible for these absorption. So as you can see, here we have our carbonyl group and our carbon-carbon functional group. And the 1695 or 1695 per centimeter is where we would find our carbonyl group. So what you can do is use your data booklet to find the range, and that range would correspond to 1695. Again, use the data booklet to find the range that corresponds to the carbon-carbon double bond. And 1619 per centimeter would fall in that range. So this is 16 wave number, so that's per centimeter. And for part 2, you are to indicate the two types of vibrations that could be exhibited by compound D, and that will be stretching and bending. This is the end of Unit 2, Paper 2, Module 2, 2025. Thank you.